completely sure that you didn't miss any parts when we had a break in transmission, right? So let's go over it from step 4 again. Remember, step 3 is we substitute the value of y. We did that, and then we factorized sin x where it was common, and we had this. So for step 4, what we have is we divide both sides by delta x. So we do that, and immediately we have that sin x into cos delta x minus 1 divided by delta x plus cos x sin delta x divided by delta x. And then from here, the next thing is we have to showcase what exactly this means, right? So in this case, do not forget that I could take the entire fraction just as I said earlier, but there is no merit in it, right? Because I'm still going to break it. Even if I have x plus 2 divided by 3, it still has to become x over 3 plus 2 over 3. So let me just start with that. Now, the next thing you also have is that essentially sin x has nothing to do with delta x. So you can isolate it, just like you can also isolate cos x here and have it like this. The reason why I can do this is because it's a product, right? So even if I say 2x, if I say 2x divided by 3, it's still the same thing as saying 2 over 3 times x. It's still the same thing as saying 2 times x over 3. So I can isolate it anyhow I like. And then for step 5, what I have to do is take the limit, which we are familiar with. So this will be dy dx is equal to limit delta x tends to 0. Now, delta y over delta x, which is going to be equal to limit as delta x tends to 0 of this. So it will be sin x into cos delta x minus 1 divided by delta x plus cos x into sin delta x divided by delta x. Let's put all of them in a big bracket. Now let's substitute them, or let's split them, right? In this case, dy dx will now be equal to first fraction. Sin x can come out because again, it has nothing to do with the delta x. So the limit can go in, sin x can come out. So it will be sin x multiplying the limit as delta x tends to 0 of cos delta x minus 1 divided by delta x. And then here I also have plus cos x multiplied by the limit as delta x tends to 0 of sin delta x minus or divided by delta x. Now, in both cases, we see that the denominator will be 0, which means that it's going to be undefined. Now, if it's going to be undefined, our mind goes to L'Hopital. L'Hopital rule tells us that differentiate the denominator separate, differentiate the denominator separate, the new result you have, take the limit. So that's exactly what we are going to do here. So if that's the case, don't forget that my variable in this case is delta x, right? So I'm taking the differentiations based on delta x as a variable. Think of delta x as your x in this case, right? So don't think of it that delta is separate from x. No, it's the same entity. So if I differentiate cos delta x, do not forget at this place you also have cos. So the differential of cos gives you minus sine, right? So that will be sine x limits as delta x tends to 0. Here you'd have minus sine delta x, then differentiation of 1 is 0, so that goes. And then denominator differentiation of delta x gives you 1. And then on the other side, you have plus cos x limits as delta x tends to 0 of differential of sine gives you cos delta x divided by 1. And you evaluate again. Now, the denominator is 1 in this case. So it means that it cannot become undefined. Now, if you evaluate when delta x is 0, sine 0 is 0. 0 is a special angle. So sine 0 is 0. So it means that all of this side goes away. If you evaluate as delta x tends to 0, cos 0 is 1. Cos 0 is 1. So it means that this will be cos x times 1. So that immediately tells you that dy dx is equal to cos x, which is what we have in the original sense. So this is how to evaluate y equal to sin x by first principle. You can also try to evaluate y equal to cos x by first principle, and you will see how it looks like. Now, what is the most important thing that you can see about this? The most important thing you can see about this is, first and foremost, the existence of the first principle is to show you the long method that is passed through in order for you to have those short formulations that you have. Are we together? It is not meant to replace the formulations. It is just meant to strengthen your faith in those formulations. Just like how completing the square method is not meant to replace quadratic formula, it is meant to strengthen your faith in the quadratic formula, because you know that you use the completing the square method to get quadratic formula. That's the same thing that you have here. And that is why first principle is a technique that it is very, very good if you know it. The reason being that even if you come across um, functions that you don't know how to differentiate them in the standard form, you can always go back to basis and differentiate them with the first principle, and you would most likely get your result immediately, especially if it is one of the forms that you are familiar with, whether it's algebraic form, trigonometric form, exponential form, logarithmic form, as the case might be. So this is something that you should also keep at the back of your mind. We have these different ways of writing, we have these different ways of solutions, so that we can also help ourselves understand why we have those standard forms, right? So why I'm saying this is, it is enough for you to practice your first principle using algebraic and, of course, trigonometric forms, right? You do not need to take overtly complicated functions when practicing first principle. Your knowledge of how to solve by first principle is what you need. When you have overtly complicated functions, use your standard functions to solve them instead of trying to solve them by first principle. For instance, if you are given that y is equal to 8x raised to power 7 plus 32 over 3x raised to power 4. There is no need for you to say you want to start evaluating this by first principle. You can definitely evaluate this by first principle, but it will be a complete waste of time. Instead of this, you could just use your standard form and know that dy dx will simply be 56x raised to power 6 plus 32 over 12 x raised to power 3. And you're done. Or you have 22 times 4 over 3 x raised to power 3, and you are done. So the standard forms are there to save you time, while the first principle is there as proof of concept, proof of knowledge. So, and that's why you see that even in theory exams, and they are asked that differentiate this by first principle, the functions you'll be given will not be complicated functions, because what they just want to see is you know how to solve by first principle. So they will not give you overtly difficult functions to work with. So practice with more algebraic functions, simple algebraic functions. Practice with simple trig functions, sine, cos, so that it's easy for you to. So you can also try tan, and so that you can broaden your horizons and see how it works. So we have seen how the first principle works. We have also seen why limit is very, very important to solving differentiation questions. Limit, differentiation, they go hand in hand. They are very, very important to one another. And we are going to continue to see this over the course of our next few classes. In our next classes, we will be looking at product to quotient rules for differentiations. We are starting to get into the bits, the most important bits of differentiations now. Product rules, quotient rules, function of functions for differentiations. We are going to make sure we finish every single thing there is to know about differentiations, and then we'll take every single thing there is to know about integrations before we then move to another branch. We outlined that I think about 6 branches in our previous class, and we are going to take all of those branches one by one. So you'll see that our journey from now till March is definitely filled up. So make sure to continue to practice, make sure to continue to attend classes, right? The recordings are always available through the links. Even though the link we were using before broke, you can still access every single thing we did in the class in that previous link as well. And then you can also have everything we have done so far in this link available through this link as well. So make sure to use that as a means to rewatch parts that are not so clear to you. This is where we are going to draw the curtain for today's class. Don't forget that you still have different other classes happening based on your timetable. So always remember to talk to your facilitators about it. If you also come across any question on first principle or on what we have talked about that you don't ask questions on, you can send it to your facilitator and I will make sure that it gets across to me so that I can provide you responses. Thank you very much. I will see you in our next live section.